welcome to my talk, Brokenwire, Wireless Disruption of CCS Electric Vehicle Charging. As Alfred just said, I'm Sebastian. I'm a research associate and final year PhD student at the System Security Lab, University of Oxford. And this paper was joint work with my colleagues Richard Baker from Oxford, Martin Strohmeyer from AMA Swiss Science and Technology, and Ivan Martinovic, also from Oxford. So we all know that electric vehicles are everywhere. So as we all know, the numbers of electric vehicles increases basically every day. So we need charging parks like the one I showed here on the slide. This is just an example of one of the high-performance charging parks in Germany. But electromobility goes even further, right? We have now electric trucks, which use also or are fully electric and need to be charged. We have buses, so public transport is now also fully electric. This is another example from Germany. This is in Hamburg, a bus depot, and it's probably hard to see on the slide, but there are wires hanging down from the top, the blue wires, which are actually charging cables. So all of the buses you can see here are fully electric and they need to be charged. But some companies are even going further, and this is an example of a fully electric ferry in Bangkok. It uses 28 charging cables simultaneously to charge the ferry. I can imagine it takes quite a while to plug all these cables in and out again. But yeah, we see like there are loads of different vehicles actually using or are electric now. And this is just another example, which is ABB now advertising they want to make mining greener and want to electrify the vehicles in mines. So why did I show you all these examples? Well, all of the examples I just showed you have one thing in common. They use the same charging technology, which is known as the combined charging system. So what is a combined charging system? Well, it's the most used DC fast charging standard in Europe and North America. There are actually two different plug types. So on the left, you can see the CCS Combo 1, which is mainly used in North America or the US. And then there's on the right, the CCS Combo 2, which is used in Europe. They're exactly the same technology. They use exactly the same underlying technology. It's just a different plug shape. I don't know exactly what the reason was for this, but yeah, the important bit is it's exactly the same technology. So why do we care about CCS? Well, CCS uses power line communication. So you might remember these small adapters you can buy for as an alternative to Wi-Fi for your home. You plug them into the wall and you use the power lines to actually bring internet into another room. It's kind of exactly the same technology. So why does the car even need this? Well, while the car is charging, there's a continuous communication going on between the car and the charger. For example, the car tells the charger how much current it needs, the maximum voltage, state of charge, battery temperature. A lot of also safety critical information is exchanged. From previous work on electric vehicle security and CCS security, we actually know that PLC in EV charging and the design of the CCS standard and using this PLC technology leads to a uniquely high quality unintentional wireless channel. So what does this mean? Well, actually you can just receive the signals. They're transmitted between the car and the charger with the software-defined radio, as shown in a paper presented at Usenix 2019. So we were wondering, well, if the charging cable is an unintentional antenna and we can actually receive the signal, can we also inject? So we were wondering, can you inject into the cable to make a charging session stop? For example, one reason would be you arrive at the supermarket, someone is charging, but you need to charge as well. And if you could disrupt the charging of this vehicle, you could actually remove the charging cable and charge your own vehicle. Because for some reason, most of the vehicles usually unlock the charging cable as soon as the charging is interrupted. But we could go even further. As I just showed you, there are buses, entire fleets, fully electric. So someone could aim to disrupt an entire fleet. In fact, in Oxford, DPD, the delivery or the parcel delivery service, only uses fully electric vans. So imagine you could just deny charging of their entire fleet. They would arrive in the morning and none of their cars would be charged. This would be a huge financial loss for them. And then going even further from there, unspecific disruption could be the goal, where at some point we integrate EVs even further into our critical infrastructure, right? We talk about bidirectional charging, having the car as a buffer, and if you disrupt this communication, you can't talk with the grid, and you don't know how much electricity you need to feed back into the grid. You can't charge, and we might cause grid instabilities. So here we are in the area of like critical infrastructure, which has massive impact. Again, from previous work, we kind of know what capabilities the attacker needs to inject. It's kind of the same for receiving. We need to have access to off-the-shelf equipment, so software-defined radio, which can work in the same spectrum power line communication is working, and little to actually no digital signal processing knowledge, because initially the idea was disrupting this communication by injecting just broadband noise. However, we then realized it's getting quite interesting, because HomePlug Green PHY, the standard used in CCS for charging, uses medium access control, CSMA CA, so carrier sense multiple access collision avoidance. This means if someone on this like wire is communicating and the communication node receives this information that someone is communicating, the node will back off and not transmit and wait until the other transmission has finished. So the standard defines that actually the detection of an ongoing communication is the detection of a preamble. And it's enough if a preamble is detected with a total signal-to-noise ratio of 2 dB, which means a preamble which is that just needs to be 2 dB above noise. So if we combine this information from the standard with actually the previous research, we came up with Brokenwire. So the idea was, can we trigger wirelessly over the air this CSMA mechanism? So let's have a closer look how Brokenwire actually works. So here you can see just an ongoing communication. This is just a frame captured. So you can see the preamble in the beginning. That's the bit the modem has to detect, and if the modem detects the preamble, it will back off. And some of you might have already spotted it, but there's actually another preamble. It's just right there. It's extremely hard to see this preamble, right? But if we do a correlation with like the preamble template, we can easily spot this preamble, and this would actually be sufficient to trigger this back-off mechanism. So we did some tests. We were curious, does this actually work? We got some HomePlug Green PHY PLC modems. On the left, this was our electric vehicle. So the big PCB was the modem. The small one is a Raspberry Pi, which was just running iPerf. And then on the right, it's our charging station. Again, just a HomePlug Green PHY modem with a Raspberry Pi running iPerf client in this case. So we had an ongoing UDP connection or communication between these two Raspberry Pis via power line communication. And we then measured how much packet loss we receive if we emit a preamble and if this preamble couples onto the charging cable. On the attacker side, we used off-the-shelf equipment. You can get it on Amazon. Actually, it's a bit harder now to get this because of chip shortage, but some while ago, you could just easily get a Lime SDR for $200 on Amazon. We had a small amplifier, but that's not necessary, and I will talk about this in a second. And our antenna was just an antenna balloon and just a bunch of wires. So it was really, really simple. And this is where we did some experiments in our social area, actually. And we see the HPGP modems in the back. So this is where the car and the vehicle were charging. And then we had the attacker in the front. I think in this case, this was roughly 10 meters distance. And yeah, we emitted the preamble and we got these results for different distances. So it's exactly the same graph, just on the left, it's in dBm, and on the right, it's in milliwatts. And to our surprise, from 10 meters away, we had to emit the preamble with less than 10 milliwatts to actually couple onto the wire and trigger this back-off mechanism. So this meant as soon as we emitted the preamble, we could see the packet loss going up in the UDP communication until basically both modems just stopped communicating because they were waiting for the ongoing transmission to finish, which never happened because we were constantly emitting the preamble. So we were quite curious, does this actually work on a charger? I mean, the HomePlug Green PHY modems we used had exactly the same chip that are used in real cars and chargers. It's a Qualcomm chip. And so with our collaborator ArmaSwiss, we did some real-world experiments. So we got the hardware we just saw in a lab environment into the back of a car. So you can see the Lime SDR again, an amplifier, our antenna, which I mentioned is just a bunch of wires. And we had to use UPS for a power supply, but we later changed the setup and we can actually power everything from a power bank, for example. So you can easily fit this in your backpack. Yeah, and then we tested different scenarios. So we wanted to know, can you actually disrupt and leave? What happens if you disrupt the real charger? And we found out once you disrupt the real charger, it actually stays disrupted. It goes into an error state and will not continue charging until you go there, you unplug, you plug in again, you touch your RFID smart card or start charging via the app. So the attacker needs to be physically present for a very short period of time. I mean, we're talking about a distance, right? It's a wireless attack. But you need to be there for, let's say, like 1.5 seconds, emit the preamble, the charging is interrupted, and it stays interrupted. So that's why we looked at the first scenario, which is a drive-by attack. So we put everything in the back of a car and just passed by a car that was charging, and it immediately shut down the charging, and you could just leave. So this is quite dangerous. If you, again, think about the fleet denial, let's say you have the TPD depot with all the vans charging, you put the stuff in your car, you pass by. I mean, you don't care about physical barriers, right? The signal propagates through walls because it's RF. So yeah, you go there, you emit, you disrupt, and you leave. But yeah, we tested other scenarios like if the angle, how the environment influences the required power. And then in scenario 5, which is also quite interesting. Actually, sorry, let me go back to scenario 4. We also tested multiple vehicles at once. So yes, even if you have like 3 vehicles charging all at the same time, you emit the signal, you can actually hear how the chargers, the fans switch off immediately after each other. And then scenario 5, we tested the distance. So how far can you go away having a given power budget? So we set our limit to 1 watt, which was according to government regulations. So with 1 watt amplification, or just below 1 watt, how far can we go? And we tested loads of different cars. And I would like to stress at this point that this is a standards issue, right? And that's why we don't reveal which cars we tested, because it's not a single manufacturer affected. It's everyone affected implementing the standard. And so, yeah, we tested loads of different cars. And you can also see it doesn't depend on the charging capacity, how much you can, or like how fast you can charge. It doesn't depend on the price or on the class. So yeah, throughout all of them were vulnerable. We also tested 20 chargers. Again, same thing. We don't disclose which chargers we tested just because it's a standards issue. So here is a photo of real world testing. We had our 1 watt power budget, and we basically slowly went away from the charger, and we tested how far can we go. And yeah, in this specific scenario, it was roughly 50 meters. And as soon as you start up the Docker container and you start emitting the preamble, the car shuts down. So what can we do? I mean, obviously, the first countermeasure that comes in mind is shielding. But actually, shielding doesn't work here. I just want to remind you, we need to emit a preamble or inject the preamble onto the wire with just 2 dB above noise, right? That's very, very low. And even if you shield the cable, the signal might couple onto the PCB traces or onto other power lines which the charger is connected to. So shielding doesn't work. And we actually tested different cables, like twisted pair shielded cables, Ethernet cables. And yes, it makes the attack more harder or more difficult, and you need a little bit more power. But we talk about, instead of 10 milliwatts for 10 meter distance, we now need 30 milliwatts. That's still nothing, basically. Yeah, and I would just refer you to the paper if you want to learn more about like the shielding and what different cables we tested. So another countermeasure would be a firmware update. And we would still like to talk to people from Qualcomm to actually find out and know, is it possible? Is the correlation and like the CSMA CA mechanism implemented in firmware, or is it in the RF front end? So does it require hardware changes, or can it actually be fixed via software update? And finally, it's not really a countermeasure to stop the attack, but it would make the impact much less, because if you would just re-authenticate the charging automatically as soon as the communication can continue, you would actually avoid situations where an attacker just drives by with the car and the hardware and knocks out the entire charging park. And especially because CCS or the plug we saw earlier has what is called the proximity pilot, and the proximity pilot, if you can measure that this circuit is constantly closed and you know the plug hasn't been unplugged and everything is still fine, you should just, or you could just continue the charging session. So what is the conclusion here? I mean, seems like CCS is vulnerable to wireless attacks. So not just eavesdropping, but also injection. Right now, as I mentioned, CCS is one of the, or is the most common DC fast charging standards in Europe and North America, which means roughly 12 million vehicles are vulnerable right now to this attack, including buses, trucks, boats, you name it. And finally, probably just not use PLC for critical communication such as the charging loop. Thank you so much. If you have any questions, please feel free to reach out. We also now made our the attack details publicly available. So basically today, the embargo period of Brokenwire ends. So you can go to our GitHub repository, check out our source code, download the Docker container. If you have a Lime SDR, you could just go straight and test it yourself, but don't do it on a public charger. And yeah, please feel free to ask questions.
Just curious, how does this get fixed in the real world?
That's a good question, and I can't give you the exact answer to this. I mean, the manufacturer is working on it, and we were involved. So we disclosed this vulnerability last year around February, and we got involved in helping them to fix this vulnerability. But I can't give more details about how exactly.
So